With chapter 3, we are starting a new chapter, chapter 4, and this is going to be a relatively short chapter. This is on deflection of beams. Okay. Chapter 4. Okay, so this is a short chapter because you probably have seen deflection of beams before. So a concept which is kind of important for most of the things we're going to talk about in this course has been elasticity, right? Elasticity is a material property that enables the material to regain its original shape after the load is removed. Property the material to regain its original shape or configuration once the load is removed. So that's something we know about. Now there's with the elastic material, there is something called elasticity modulus, which is E, but most of the time we talk about what is known as a spring rate or a spring constant, and that spring constant is essentially the limit of the deflection going to 0 delta F divided by delta Y, okay, or dF dy. So for a beam, when there's a load F, and I've just shown a simply supported beam, but there could be other beams, and the load can be at any point, there will be a deflection, and that deflection, let's say, is Y, then we can write the spring constant or spring rate as F divided by Y. And if you think of this as X, then this is actually a function of X. So for different X's along the beam, you will see that the deflection Y is different, which means that the spring constant or spring rate K is going to be different. It's going to be a function of the distance along the beam. Now there is a corresponding spring rate for beams in tension, rods in tension, compression, as well as shafts in torsion. And this is something we've seen before. You may not have thought about it in this way. So I'll just write down these formulas and then we'll move on to deflection of beams. So for tension, compression, and torsion, we have the following formula. So we've seen that Young's modulus is force divided by strain, but the strain is delta L divided by L. And so we can write F divided by delta L. No, I'm missing something. This should be stress. So force divided by area, right? So E equals F L delta L times A. And so I can just put it in this form. F divided by delta L, which is my spring constant. And you can see that it's simply E A divided by L. So E is the Young's modulus, A is the cross-sectional area around which the force acts, and the length, L is the length. It's a K is a material property. So this is what you should write if you are asked to find the spring rate of a beam in tension or compression. Of a beam in, or sorry, a rod in tension or compression. So that would be tension compression of a rod. Okay, so we can also write a similar formula for torsion. I'll just quickly write that down and move on. We've seen these formulas before. So for torsion of a shaft, okay, we wrote down a formula which relates the torque to the angle of twist. So G J theta divided by L. Okay, this is a formula we derived, see last chapter in this section 312. So then the spring constant now is the spring constant is going to be it's essentially a torsional constant, is the force for a being under torque is T divided by the angle of twist, and that is Gj divided by L. So that's L. So that's my spring rate. So the point here is that you can find the spring rate very easily by taking the force divided by the change in length, or in case of torsion, it's torque divided by the angular deflection. Okay, and so that's what the spring rate, and you can see that the spring rate is a constant. The moment you give me J, which is the polar moment of inertia, G and L, K is constant. Same for this one, right? E is a constant, A cross-section area is constant, length is constant. Now, sometimes if you have a tapering shaft, then A is going to change, but that's fine. It's constant along, for a particular section, it's constant. Just like it is for the beam, which is, it's going to be a function of X. Okay, so we're ready to start diving into deflection of beams. So what we're interested here is if we have a beam and we subject that to, it could be a shear force as well as a moment. I'm just going to put a M here, but could be a load, concentrated load, or a distributed load. And that M will cause the beam to deflect. Okay, now for such a beam, we've derived some formulas from, this is from the previous section, from previous chapter. Following. So the moment M divided by I equals E divided by R equals the normal stress divided by the distance from the neutral axis. Okay, now let's take this part and rewrite it like this. 1 divided by R is equal to M divided by ER. Just rearranging things. Now, 1 divided by R is actually called the radius of curvature. Okay, the radius of curvature, there's a formula for that, and you might have learned about this formula when you did in dynamics curvilinear coordinates. Rho is given as follows. It's d square by dx square divided by 1 plus dy dx squared, 3 divided by 2. Okay, so it looks very complicated. We'll do a simplification, which is as follows. So if you have a beam and you deflect it because of a load or a moment m, show some deflection. Right? This angle is theta, which is nothing but dy dx. Right? So when you have a stiff enough beam, dy by dx is small enough. It's not like it's going to bend by a whole lot, because if you see a beam bending so much a lot, then it's probably not going to be a good load carrying member. What if the bridge just bends a lot, right? So we will consider the cases where there's elastic deformation. So the deflections are small. And so one is much, much bigger than theta, which is equal to dy dx. And so what we can do here is we can say that this term, the numerator is essentially 1. So this is close to 1 or almost equal to 1 because of this fact that the deflection is not that much. And so I can write rho equals d square by dx square. And so if I plug that back in this formula, I have that equal to m divided by ER. Okay, so what's going to follow is basically taking this formula and writing it in different ways. We have M, but we could also have a shear force V. We could also have a bending load, uniformly distributed load W or Q, and then we need to relate all of them to the deflection Y in some way. Okay, so what I can do is write the following. So I just wrote down M equals EI d square y dx square. So what I know now is that the shear force is the rate of change of bending moment. And so that is equal to d cube by dx cube. The next thing to note is that Q, which is load by unit length here per unit length, is dv dx. And so if I take the derivative of v now, which is written on top of it, it's simply ei d raised to 4y dx raised to 4. Okay, so what the thing you want to use to solve problems is basically the following things, which is theta is dy dx. That's the first moment. The first derivative of y. The second derivative, as you can see here, is going to give you m divided by ei. So m equals ei d square by dx square. If you take the next derivative, you get ei d cube v equals ei d cube by dx cube, and then q is the next derivative, so ei d raised to 4 dx raised to 4. So those are the things which you ought to know when solving a problem. So either you know Q, you know V, you know M. Once you know those, you just put them in the formula there, and then you get the first, second, third, fourth derivative, and then you have to keep integrating those equations to get Y. So we will use, use one or more of these equations to solve for Y as a function of X, where X is the display or the distance along the beam. You could also solve for dy by dx as a function of X. So that's the slope. Okay, so let's do a few problems on how to apply these formulas. So cantilever beam, let's say that this point is A, and let's just choose the origin to be right here. So Y. Then let's say that this is L. Okay, so the question is compute Y as a function of X and dy by dx as a function of X. So this is the deflection and the slope. And then once you do that, find the deflection and slope at A, where A is this point, the tip of the cantilever. So for a problem like this, you have you can start in number of ways. You can take any one of this formula, either this one, or this one, right? If you start with the first formula M, you want to do is you want to cut a section and then write the moment, which will be a function of X, and then integrate the equations 2 times, because that's how you will get Y. If you want to start with the second equation, V equals EI d cube by dx cube, you want to draw the shear force diagram and then integrate that equation. So you'll have to integrate 3 times. If you want to use the fourth one, then you'll have to use the fact that the distributed load is what you look at, and the distributed load here is 0. So you could start with that also. Now, so though you could start with any of those 3, it looks like the easiest one is probably the first one, M equals EI d square by dx square, because I only need to integrate twice, which means that when I do the integration, I have two constants of integration, which I need to evaluate. So I'll just stick with that. But remember that you could use either of these 3 formulas and proceed, and your answers will be the same. So let's start with this formula. Let's use M equals EI d square by dx square. So I need to find M. That's the thing I'm interested in. So let's draw the bending moment diagram. By this diagram, I'm not trying to draw the complete bending moment diagram. I'll just cut a section of the cantilever beam, right? And then that distance, let's say, is X. This is our point A. This is the load P, and there's a moment which is now unknown. Now, if you go back and refer to the how you draw the bending moment diagram, loads which are clockwise, the way I've shown, are positive, right? So, sorry, counterclockwise positive. So that's counterclockwise positive. And I'm taking moments about this point, right? Moment, this. So that P will induce a moment. The moment arm is X, so P times X, but that P times X is going to also induce a counterclockwise moment, so it's also be positive. And so the net moment should be equal to 0, and that helps me to solve for M, is minus P times X. Okay, now let's go to the bending equation, which I just wrote down. Which is this one. And I'm going to sub in the value for M. M is minus Px equals EI d square by dx square. Okay, so P is a constant, E and I are all constants here. So I just left with integrating this equation 2 times. Okay, so integral x dx equals EI. Okay, now the way I'll write this as is d dx of dy by dx, right? So d, the derivative of dy by dx with respect to x is d square by dx square. And then I just do dx. So this is the same as this. I just rewrote it just to make it easier to see how you get the next step, which is the integral. So we have on the left side p times x square divided by 2. That's the integral of x. Okay. And since you're integrating something, you need to have a constant of integration. So C1, which is clearly an unknown, we need to find that, equals EI. So dx, well, what happens is basically you're left with d by dx. So the integral of second derivative is the first derivative. That's what this is doing. But we're not done yet. We still need to find what y is. But let's just note this down because we'll need this equation later on. So let's integrate it again. Minus p divided by 2 x squared dx plus c1 dx equals e I dy dx times dx. Okay, so then we have the integral of x squared is x cubed divided by 3 plus c1x plus c0. This is the constant of integration when we integrate this whole expression, right? There would be a constant equals EI. So now the integral of the first derivative is the value itself, so it's y. Okay, so let's just call this 2. Okay, now we need to find these two constants, C1 and C0. So once I find these constants, I can evaluate what y is. And similarly, if I know C1, I know what dy by dx is. So the way you find the constants is you need what are known as boundary conditions. You need to know something about how the beam behaves. So for example, looking at this beam, what do we know about the beam? Well, we know that at this point A is going to be deflected, it's going to move down, and it's going to have a slope, and we don't know what those slope and deflection A is. However, we do know that this point is not going to move, right? Because it's fixed to the wall. So the deflection at x equals L is 0. And also the deflection, the first derivative of y with respect to x at this point is going to be 0 because that point does not deflect. It deflects, but the slope is 0. So the slope here is 0. It will be something like this. So y is 0, dy by dx is 0 at this point. So let's take this and then try to use this fact. So y equals 0 at x equals L. Rather, did I put a small L? No, small L. Okay. So let's just use this fact in equation 2. This is my equation 2. So I'm going to put x equals L. I'm going to put y equals 0. So x equals L plus C1L plus C0 equals EI zero. So this is from, okay. Also, we know that y equals, sorry, dy by dx equals 0 at x equals L. So at this point, again, it's 0. So I can look at expression 1, which is right here. I'm going to put x equals L and put dy by dx is 0. So putting that down. PL squared divided by 2 plus C1 equals EI times 0. Okay, so this equation, so this is from 1. So from here, we can write C1 equals plus PL squared divided by 2. Okay, if we call this as 3, now we can put the value of C1 here and then find what C0 is. Let's just do that. So from 3 minus P divided by 2, L cubed divided by 3 plus C1, which is PL squared divided by 2 times L plus C0 is 0. And solving for C0 gives minus PL cubed divided by 3. Okay, so once we have C0 and C1, we effectively have solved for the slope and deflection. So y is 1 divided by EI px cubed divided by 6 plus PL squared times x divided by 2 minus PL cubed 3 and dy dx equals, so for dy dx, all you have to do is just take the derivative of that, or you can look at the expression and then sub in the value. It's easier to take the derivative of y. Two plus PL squared divided by 2. And then at x equals 0, that is at a, right? We need to find the deflection and slope at a. We have y is minus PL cubed 3EI. So all those are answers. So this is one answer. This is the other one. So what you can do is you can see that if you want to find the spring rate, which is P divided by Y at A, then you simply move this down, and then that will give you 3EI divided by L cubed. That would be the spring rate. Okay? And you can see that the spring rate is going to be a function of X. So if you write K equals P divided by Y, so P is here, Y is here, you'll see that it's basically some nonlinear function of X. The moment you put X, you can find the spring rate. So the K is a function of X. We'll write this down. Write it down, but that's how you find it. So this is pretty much what you need to do, which is draw the shear force or wheeling moment diagram, the equation, and this integrate. There is, well, it will take a lot of time, but let me just, what I'll do is, let me just write down. I mean, if you want, here's an example. I won't solve this because it'll take me way too much time. But I encourage you to try this out at home and get the answer which I got. So here's another problem, but you should solve it home. I won't solve it here in the interest of time. This is the one with uniform load of W. Okay, so the question is find y of x and dy dx is a function of x. And clearly this is x, this is y. And the answer is as follows. Okay, so do this at home. The hint is, if you draw that free body diagram I showed you, and you try to find what the moment is, and the formula for the moment would be W divided by 2. And then once you have the M, it's just a matter of writing that equal to E I T square Y dx square. And integrating it twice, it's a bit more complicated because you have now you have this x and x squared. Okay, there's one more problem I would like to do, which is a different kind of way you need to solve this. I'll do that, and we'll stop there. Okay, so this is problem 2. Try it at home. Okay, so here's the third problem, which will consume the rest of the class. So simply supported beam. But now the load is somewhere here. Okay, so let's give this names. Let's say this is A, this is B, this is C. Okay, so the question is find the slope and deflection at C. So this problem is slightly different from the other in the sense that, as you see, you cannot, you'll basically have a change in moments as you pass through C. So the left side, there's a different equation from the right side that is across C. And so the way you need to solve it is you need to consider one section of the beam, A to C, write the moment equation, integrate that twice. Okay, that will give you 2 constants. And then you'll have to write another equation for C to B, integrate that twice, and you'll have 2 more constants. So you'll end up with 4 constants, and then you need to find those 4 constants from the way this problem is set up. So that's why it is slightly different. So I'll just go through it. And this will be the last problem we'll do for deflection of beams, which involves tedious integration. So for that, what you do is you draw a free body diagram first, because we're going to draw a bending moment diagram. I'll leave the details here, but write down the answers, because by now you should know how to solve for the forces, right? So VA in this case is 3P divided by 4, and VB is P divided by 4, such that the sum is equal to P. That's the first piece, right? Second piece is, let's do deflection for section between A and C. So what we do is literally cut the section between A and C. So now we would have this VA acting upwards, and then we want to find the moment, right? So I just drew the M, which is an unknown now. X is this distance. This is very similar to how we drew a bending moment, right? So just, it came from here by doing Fx equals 0, Fy equals 0, and moment equals 0. So I didn't write that because I assumed that you'll do that. No problem. Yeah. So we cut the section. Now again, M is counterclockwise, so it's positive. The moment due to VA is going to be this way, and so it's clockwise. So 3P divided by 4 times the moment arm, which is X. And so we put a negative sign here. So positive for M, negative for VA, moment due to VA equals 0. So M is 3P divided by 4 times X. Okay, so now we are all set. We write EI d squared by dx squared. Okay, so let's just integrate this expression. Once, so 3P. So I'm going to skip writing the integral. I'm just going to write the integral. Okay, saves me some time. So integral of X is X squared divided by 2 equals EI dy by dx. And then you can put the constant anywhere you want. Let me just put it. Let's put it here. Just put it in the. Just put it here. C1 equals integrate again. So we would have 3p divided by 4. The 4 2 is 4 times 2 is 8. So x cubed divided by 3 plus c1x plus c2 equals ei y. So that's my 1, 2. Yes, I got two constants. The issue now is that when I try to find these two constants, I won't be able to find both the constants. In fact, I only can identify one condition, right? The only condition I can identify is that at x equals 0, which will correspond to a, the y is equal to 0. That's the only thing I know. I know nothing about point C yet. So I can't really evaluate that expression or find the constants with any of those two. The deflection at a is not equal to 0. So I can't use that. So that's where I can't do more than that. So let me just take the next piece, and then I'll show you how that piece and this piece can be used to find all four constants. So let's take the deflection bit for section between C and B. Here's the beam beyond point C. PA is 3p divided by 4. This is my m. This is x. So I need to write the moment equation. So plus m for this one, 3p divided by 4 times x, but that's clockwise, so negative, and this p will induce a counterclockwise moment. So I'll write p times this distance. So it's going to be L by 4. So x minus L by 4. And then it's going to be a counterclockwise one. So that's what it is. And so m equals 3p divided by 4 minus. Okay, so then I need to integrate this 2 times. Okay, so since I'm running out of time, I'm just going to write the expression down as I have it in my notes. So what I get is E I dy dx equals P divided by 4 Lx minus square divided by 2 plus C3, and then integrate again. EI y equals P divided by 4 Lx squared 2 minus x cubed divided by 6 plus C3x plus C4. Okay, so now, as I said, we have not one, not two, but 4 constants, and we need to find the 4 constants. So let's call this 3 and this 4. So we need 4 conditions, right? Unless we have 4 conditions, we cannot find the 4 constants. Question: why was the L dropped in the second parenthesis? How? Which parenthesis? can you, somebody said, why was L dropped in the, can you tell me which parenthesis you were talking about? I made a mistake. Yeah, this is incorrect. This is dimensionally incorrect. So good catch. That should be x squared. My bad. Because yeah. Okay. So let me just state this, and it's already I'm out of time. So the way we found four constants is, first we said x equals 0, y equals 0, right? For the beam, here x equals 0, y will be 0. Also x equals L, y equals 0. So we can write x equals L, y. So that will be equation 2 here in my notes, equation 4 in my notes, this one, because remember that equation is valid for the sections after C. I need to generate 2 more equations, and this is where I need to use something about the point C. So what I do is I note that at C, since this connects, the left side and right side connects, at x equals, in this case, L divided by 4, y due to left half equals y due to right half. So what I need to do is I need to take equation 2 here, make it equal to 4 at x equals L divided by 4, right? That way there's continuity and those connect. So that gives me one more constant. I need a fourth condition. Here the fourth condition comes from the slopes, which is at x equals L divided by 4, the slopes should also be equal. So that means 1 should be equal to 2. X equals L divided by 4. Okay, so I don't have time to write the expressions, but I'll finish it up and I'll post the notes.